Who here has used Python before? Almost everyone. Okay, who here has used NumPy before? A little bit. One. Okay. Okay, that should sort of help gauge.
Don't test my knowledge.
No, that's okay. It's okay.
How does pandas compare with R?
How does pandas compare with R? Okay. Yeah, I can talk about that. I don't have any slides directly with that, but we can talk about that.
For somebody who's interested in data science, is Pandas a good place to kind of get started?
Yeah. Let's see if I have it up here somewhere.
So the keyword that got me was ETL.
Uh-huh.
How much of detail does Pandas do?
So if you look at like your traditional ETL systems like Kettle or something like that, where it defines a data flow and everything, Pandas isn't going to give you that. What Pandas is going to do is allow you to tweak and pull out data and clean it. So I mean, if you look at like the big data Borat, who says like 80% of big data is garbage with munging data or something like that, that's what Pandas is going to allow you to do. So yeah, I guess I don't know if anyone else is coming, so let's just get started here, and I'll sort of address those questions and more. If you have questions, feel free to ask them. So my Twitter handle is Dunder M. Harrison. Let's see here. And a little bit about me. I'm the co-chair of the Utah Python group. We meet on the second Thursday of every month up at a company called Needle, which is at the point of the mountain. So you guys are welcome to come to that if you want to. We usually start around 7. And we don't just talk about web stuff. We talk about other stuff like pandas. A lot of people seem to think that everything that's important these days is Web 2.0 and that sort of thing. And Python certainly has its share in that. If you look at like startups who are starting up in the Bay Area, a good percentage of them are using Python on the back end. Probably the second most popular startup language, I would say, second to JavaScript, and there's obviously a reason why JavaScript would be number 1. So, but Utah Python, we're pretty friendly. We meet every month. I'm currently a consultant, so I have 14 years of Python experience across various areas. I guess most recently I was doing data science and testing and provisioning architecture at a company in Salt Lake. Previously, I've also done business intelligence, web developments, worked for a search company, and open source stack management. So if you're interested in more about me, there's my website. I've written a couple books on Python. I'm currently producing a course on Python. So if you or your company is interested in that, it should be up for sale soon. Here's a brief outline of what this is going to cover. We'll talk about series, data frames. These are data structures within pandas, how to create them, looking at data that's in there, tweaking data, filtering data, joining data, grouping data, doing pivot tables, and plotting data. So we'll start off with an introduction. If this were a Perl class, it would be, okay, you've got some CSV file or tabular data. How do you use regular expressions to tweak that, right? Because Perl, that's the weapon of choice. And it seems that over the past couple of years, Pandas has sort of come out as the weapon of choice for dealing with tabular data in Python. And if you go to the Pandas website, it says something like this, or it did at one point. Pandas is an open source BSD licensed library providing high performance, easy to use data structures and data analysis tools for the Python programming language. I think that's a lot of jargon. I would probably characterize it something like this, which may be even more jargony. A NoSQL in-memory database using Python that has some SQL-like constructs. And it adopts many NumPyisms. So even if you're coming to Pandas as a Python user, there might be a lot of gotchas because there are some things in the NumPy world that aren't necessarily clear or evident to Python developers or people who are used to Python. So I'll try and cover some of those as I talk about it. Pandas grew out of the financial sector for doing time series analysis and is modeled on this data structure called data frame, which is stolen from R, which is, one can think of a data frame as tabular data. So you could think, who here's used SQL before? Okay, so you can think of a data frame as a table in SQL database. Or one way to think of it might be Excel spreadsheet, right? It's got rows and columns. So Pandas allows you to get data like that and do operations on it. So why is it speedy? Because it says it's high performance here. It's built on top of Python and NumPy. So NumPy has lower level data structures that are more compact than standard Python, so you can fit more memory in. And a lot of the data science stuff now is around big data. Pandas doesn't address big data, but it does address small to medium data, where that depends on how big your machine is and how much RAM you have. So NumPy helps you optimize, and in Python, if you program in Python certain ways using type annotations, then you can remove some of the dynamic nature of Python and get some runtime improvements. So it's currently at a point, this is 0.13.1 release. What's on the roadmap for like a 1.0 release, I don't know per se. The person who developed Python, Wes McKinney, is no longer really doing much with Pandas. He's off doing his own startup. But I shouldn't say that as to like scare you from using Pandas, because I've used Pandas for the past 2 or 3 years and it's worked out fine. There haven't been any huge big gotchas in rolling as Pandas has been updated, making code work. So Pandas includes a couple data structures inside of it. One is a series, which is a one-dimensional data structure. Another is a time series, and this was sort of the birthplace of Pandas. If you're looking at financial data, you have all this time series data, and you want to do various operations on that. And you can think of data frame as pulling in a bunch of these series into a two-dimensional data structure. And then the last one is a three-dimensional data structure you can think of as a stacked data frame. So in this talk, I'm basically only going to cover series and data frames, because time series are a specific instance of series that if you care about time series, you can sort of figure it out. And panel, I've never actually seen anyone use panel or reference it or care about it, so I'm not going to mention it other than here. And part of this talk is to say, this is Pandas. If you're going to use Pandas, how would you use it? What are the gotchas or things that might bite you as a Python programmer? Like, I'm just being straight and upfront. Pandas is useful. How I came to it, my previous company was doing BI, and I had written an ETL system and OLAP engine in Python. And then when I came to my company after that, they said, okay, do some analytics, and we use Python, so you use Python. But the previous tools I had written weren't open source, so I couldn't just take them over. And for me, it was easier just to start off with Pandas and use what Pandas had rather than rewrite my own. And so that's sort of how I got started using Pandas. And so if you're coming from an ETL perspective where you say, I've got some star schema and I've got slowly changing dimensions that change over time, and your ETL system. So ETL, for those who don't know, is extract, transform, load. It's for taking data from one system and putting it into another. Normally, if you have like an enterprise data warehouse or something like that, they'll use ETL jargon to describe this process of flowing data from one place to another. And so you can buy expensive or somewhat expensive packages that do this for you and have a GUI, and you can drag and drop things to transform data over from one system to another. And Pandas doesn't provide, for example, one of the things the ETL system might provide or should provide if it's decent is this notion of slowly changing dimensions, where if you have a dimension in a star schema and say, for example, you have a store, and the store has various properties. One of the properties of a store is the square footage of a store. If you change the square footage, like you remodel it, do you want all of your fact tables to change which store they're pointing to, or should they point to a new store or the old store? And those are things that you have to, if you're doing data warehousing, you have to keep track of. And Pandas really doesn't deal with any of that sort of thing. So let's talk about what Pandas does deal with. The series is the basic one-dimensional data structure. And if I were to create a series in Python, this data structure in Python, or maybe in JSON, it would look something like this. So I'm creating some object or a dictionary, and it's got three things that I really care about. Probably the most important is this data. So it's got data in there, and if you look at this, then here's your one-dimensional data. Somewhat interesting, it has another parallel array with data called index, which is the index values for that. In this case, they're integers, which would sort of make sense, but they don't have to be. And then it has a name, growth. So you could think of like, maybe this is a plant that's growing over time or something, and at day 0 it's half a centimeter, at day 1 it's 0.7, at day 2 it's grown a little bit more. So that's a basic series, or how a basic series would look in Python. Now if you wanted to do that in Pandas, this is how you do it. Import Pandas as PD. So this is, in the NumPy world, they like to rename imports to 2 letters or import star because they don't like typing a lot. I would recommend against doing import star. So import Pandas as PD, that's the convention they use. And on PD, there's the series object. I create one, and I pass in the data that I want to be in this series. And by default, it will create an index here from 0 through 1, 2. I can pass it a name as well. In this case, I'm passing it growth, and it will say growth. The interesting thing here about Pandas is now it's coming down here and saying, okay, your type is this float 64. And so Pandas can go back under the covers here, and it can say, rather than using the native Python type, which is going to be boxed and have overhead on top of it, it can go down and use NumPy under the covers and pack it in there. And we'll get to some of the optimizations that it can do. So again, 3 things. It has data, index, and name, even though it is a one-dimensional data structure in Pandas terms. So I mentioned the index in that case was integers, but it doesn't have to be. It can be strings. So I can have the index be A, B, and C, and that's how you would do that. So again, these are parallel arrays that go together. And you can start doing things with these series once you have them. For example, I can dereference something, so I can pull off something at location 1. So that would be this guy here. There are also various methods on a series, so I can say mean, and that will give me the mean of all of the elements in that. And there are a ton of other ones. And so as I go through this, you'll sort of see what we do. When we pull out data frame columns, we're talking about series here because the data frame columns are series. And so some of the stuff I do later on are actually methods on series rather than on data frames. Another notion of Pandas that might not be familiar to someone who doesn't have a NumPy background is this notion of Boolean array. So if I have a series, I can say series greater than ser.median. And if you're looking at that from pure Python, that's kind of hard to parse. What would you think that would do in Python? True? Return a true or a false, right? In this case, what it does is it says, you have this series of one-dimensional data, take the median of all that, and for every value in that, return a Boolean for the index, whether it's greater than, whether this value is greater than the median. So if you look at the data here, 0.5, 0.7, and 1.2, the first two are less than the median, and the last one is greater than the median. So it creates this Boolean array, an array that has Boolean values in it. You can look at the data type here, and it says Boolean. And where that comes in useful is now you can pass that Boolean array in as a mask into an index operation on your series and filter it by that. So I can say, here's my series, here's an index operation on that. I'm passing in this Boolean array. And so filter out everything where this was true. It was only true for C, so it's going to return 1.2 there. And so you can build up these arbitrarily complex Boolean arrays and filter stuff that way. And so this is sort of interesting, right? Because here I can say ser1, and that takes out the first guy, but I can also say ser A, and that takes out the first, this guy here. Sorry, ser1 took out the second guy. This is the first guy. So again, as a Python person, some of the overloaded and magical nature of pandas isn't readily apparent to you, or isn't what you would expect, because Python, if you say import this, it says explicit is better than implicit, but a lot of pandas isn't explicit per se. Okay, like I said, there are many methods on series. You can do iteration, you can iterate over a series, you can do arithmetic operations on it. So if you have a series and you say series plus 2, that goes through every element-wise in the series and adds 2 to it. Okay? There's CRUD operations, so you can create, update, delete, index operations, basic statistical operations, operations for dealing with duplicates or not a number values. You can sort the values, you can sort the index, you can join with other ones, you can map and combine these, you can plot them, and you can serialize them. So the Pandas library provides all of these methods for you to start tweaking data. And then you can see where the power comes in for Pandas, because now you basically, like I said, if this was Perl, it would be about regular expressions. Now, if you have this Pandas toolkit, and you have any tabular data, you can just throw it in there and start tweaking it and do all these operations on it using Python if that's your preferred tool. Okay, are there any questions about what we just talked about here? Any questions? Yeah.
So with pandas, you had an expression where you defined a series using curly brackets, and you referred to it as a series or a dictionary. And I actually did something similar, and something I wrote a while ago, and and ended up going to Stack Overflow with a question, and they said that it actually wasn't a dictionary, but it was a pandas series, even though I believe that's how you would define a dictionary. How do those two relate to each other?
A pandas series versus a dictionary?
Yeah.
So a pandas series is a class that pandas implements that doesn't derive anything from dictionary in standard Python, the dictionary that's built into Python. Yeah. So it has index operations that do indexing into the series. As you could see, they behave somewhat arbitrarily based on location and name of the index, which isn't how a dictionary behaves. But some people like to claim it's dictionary-esque because you can say stuff like del you can use the del statement with a series and an index value in the series, and it will pop that out.
So it has literally nothing to do with the dictionary?
No.
Okay.
No. And so to think of it as a dictionary, I think, is wrong, because and there have also been stuff that we'll talk about data frames that say a data frame is, you can think of data frame as a dictionary, which I think doesn't make sense either. So part of this talk is to sort of say, this is Pandas, this is the data structures it uses, and if you're trying to map those onto Python, there are some mappings, right, like this initial one, way back here. I think this makes sense to think of it. This is basically what a series would look like. This is the state that a series has, and then it has various methods that you can alter that or pull data out of that. But even though this looks like a dictionary, it's like there are three important parts of a series, right? The values, the index, and maybe this name if you care about that. There's also a data type, right? So a lot of these this was a data type of a float, and when we saw the Boolean array come out, which is actually a series, it was a data type of bool, and you can have data types of objects or strings or arbitrary data types in there. So, okay. So let's look at data frames now. So you have to understand series to understand data frames, or it helps. Basically what you can think of as a data frame now is a table with columns as series. And I think this is useful for a lot of people coming from, if you're coming from a database background, if I was going to go out and naively implement tabular data in Python, I think I would implement it row-wise, right? Where you're iterating over something, it makes sense to iterate over a database row by row. And this data frame isn't doing that. It's doing it column-wise. And if you stop to think about it a little bit, it makes sense, especially coming from like an OLAP or an analytical database point of view, to implement it in a column-wise fashion, because you can, if you have a column that's, normally you'll have columns that are types, right? So you'll have a string column, and you'll have a Boolean column, and you'll have an integer column and a float column. If you implement that row-wise, it's very hard to compress that data, because you have various different data types. But if you implement that column-wise, then you can say, here's all the Booleans, and I can implement those as a bit, and I can shove them into a bit and compress them and pull them out that way. So you save a lot. You can save a lot of space in processing that way, if you're doing analytical databases. And if you look at a lot of the OLAP databases or the big data databases, their storage backend is all vertical column oriented to take advantage of the compression that can happen that way. Let's look at this then. Okay, so again, this isn't what a data frame looks like, but this is if you were going to implement one using some JSON-ish notation or Python, this is what it would look like. And these are the important parts of a data frame. It has an index, and then it has columns in there. And columns, these look strangely similar to what the series looks like. They have names and they have data coming down. So in this case, would have like Paul and he would have some growth 0.5, and George would have growth 0.7, and Ringo would have growth 1.2. Now, that's just, okay, that's how Pandas is working. Think in terms of column-oriented rather than row-oriented. That will help you understand Pandas. And now this is how you would actually define a Pandas data frame here. You have the Pandas namespace, PD, and you just say data frame, and you pass in a dictionary mapping column names to the values in those columns. And I can say in my interpreter, okay, so I didn't explain this, but all of these slides are written as if you're typing it from the interpreter, from Python interpreter. So if you say greater than, greater than, greater than in the Python interpreter, and I say df, it will do an explicit print of that. So in this case, I've defined this data frame. I say df. Pandas, under the covers, knows how to print it out. And we'll print out something like this. We'll say, okay, you've got some index here. You've got a column that's called name that has values. You've got a column that's called growth. And it will tell you the matrix size down here at the bottom. So normally when you're going to create them, you'll probably create them something like this. You can also, so we created it from columns, which was a dictionary of lists. Alternatively, you can create them from rows if you want to. So if you're iterating over a database, you might have a bunch of rows, right, where you have a key value pair. You could throw those lists of dictionaries. If you created a dictionary for every row in there, you could throw those in and create a data frame from that, and Pandas would sort of go through and vertically optimize those for you. This is probably the most handy one here. A lot of, at least in my experience, I was dealing with a lot of CSV files, so people like Excel. CSV seems to be a pretty common file transfer between Excel formats, unless people are doing fancy things with Excel. So inside of Pandas namespace, there's a read CSV function that will do various things to CSV files. If you're dealing with NumPy, you can slurp up a NumPy array directly into a data frame as well. Okay, so a lot of the remaining examples will be based on this data right here. So we've got a couple columns here. We've got fname, which is short for first name. Here I'm saying list of these letters. So basically, I've got 6 letters here for first name. You can think of it as maybe the first character of their first name. We have last name here. We have a column called test1. It's going from 80 up to, but not including 85, and then it's got a none at the end. A lot of times in the real world, you'll have dirty data or crappy data, and you'll have to deal with it. Pandas allows you to deal with it, and we'll see some of the ways we can do that. And then this test2 guy, he's just going from 80 up to 91 and incrementing by 2. So it looks something like this. Okay, we've got our index here, and we've got 4 columns with data in it. And Pandas converted that none to this NaN, not a number here. Okay, a couple more things about a data frame that's important. If you're coming to the Pandas library and you start using it a lot, you should know these things. There are 2 axes, and they're referred to as axis 0 and axis 1. And a lot of the methods take these axes as values. Axis 0 is the index, so that's talking about going down this way, and axis 1 is the columns going across this way. There's an attribute on a data frame called axis, so you can pull off the first guy there, and it will say, okay, I'm an index, here's my index, here's my type, integer 64, and here are my columns. And it pulls off this index guy and says, here are the values of my columns, and I'm a data type object here. So that's one way to refer to these, 0 and 1, as index and columns. You can also pull them off as .index and .column.
So is any string data type object, or is that just Unicode strings?
Let me see if I parsed your question correctly.
So df columns data type is this, and so so columns is referring to a little more than just the strings that are showing up there in the list.
Yeah, so the columns is an instance of an index.
Okay.
So columns and index are both instances of an index, which is some label along an axis. Okay? And so it has values, and it also has a type. Normally in Pandas, when it's not using a numeric type or a Boolean type, it will say it's an object. Or if it's a mixed type, it could have numerical and character data in it. In that case, it would change it and wouldn't be able to do like compression that way because it can't compress strings and numbers, and it would just call it an object. Another thing to note here now is like, if you're coming from classical Python land, they always like to say there's only one way to do it, or there should be one way to do it. And now you're saying, well, now there's two ways to do it, right? I can say axis 0, or I can say index. And so one of the things that might be confusing or annoying about pandas coming to it is that there are multiple ways to do some things, and there are inconsistencies in the library, but that's just the nature of it. I don't mean to rag on it a lot, it's a very powerful library, but coming from a place where I'd implemented my own ETL systems and done a lot of Python, but not a lot of NumPy, there are a few hang-ups or gotchas. Let's look at some ways to look at the data now. So we already mentioned this. You can list the columns here, df.columns. There's a method called describe, and this gives you statistical summary of the data. So we'll go through and say, okay, so I had 2 columns that were numerical, so let's take the statistical summaries of those. So you can give me, here are the counts of the values of those. So test 1 only had 5 because one of them was not a number, so it didn't count that. Test 2 had 6 values in it. Here's the mean, standard deviation, min, and here's your quartiles and your max. So this is pretty useful because you slurp in a CSV file and you just say csv.describe, and it will tell you right off the bucket, you know, here's your summary statistics, which is probably the first thing you're doing if you're doing analytics on something. You say, what are my summary statistics? Where are my outliers? What does my data look like? You can also view the data from a terminal, and it will print it out. It has some smarts in it to limit how much it prints out. So it looks at your terminal size and will adjust how much it prints out accordingly. You can call toString if you want to spill out everything in there, which you may or may not want to do, especially if you have like a huge file. You don't necessarily want to say toString. So it sort of has safe defaults. If you've uploaded a file or loaded in a file that has 100,000 lines of code, you don't want to, when you say df, you don't want to print 100,000 rows in there, and it will only print, I think, the first 10 and then put ... and then print the last 10 for you. So that's kind of nice. Okay, we can also pull out a column. In this case, we say df.test. We can access it as an attribute here. So recall test1 was the name of one of our columns. We can just say df.test1. And again, coming from a Python world, that might not make sense, right? Because it's automatically creating this magical attribute for you, which I'm not a huge fan of magicness in Python. But if you're doing data analytics, or if you're in an interpreter and you're like looking through the data, then you save like typing 3 characters, which may be nice, right? And if you understand that convention, then it makes sense.
You can still go that other way, right?
Yeah, you can do either one of these. So either one of these will work for pulling stuff out. Okay, and when this comes out, now this is a series, and you can do all the stuff that we talked about, all these methods that series could do, you can do those. Okay, so for example, we can say df.test1.median, and that says, okay, the median of test 1 was 82, or max, or mean, or whatever you want. And now we're operating on test 1, which is a series. Here's another example. You can do correlation. So I can say test 1, correlate the values of test 1 with test 2. Basically, if you don't know what correlation means, it says if the values appear to both go up at the same time, then it should be perfect correlation, which would return a number 1. If there was no correlation, it would be 0. And if one went up while the other one went down, it would be -1. So in this case, if you recall, I described a range where both of them sort of went up, and so we do have good correlation there. But this is useful, again, if you're digging into data, or you want to sort of say, okay, I've got this spreadsheet I just loaded up. What do these values correlate or not? You can do this really easily in Pandas. Okay, let's look at like tweaking data. That's just summary statistics here. So we want to add a row for mat age. And this is how you would do that. And this seems a little verbose. And I would note that in general, Pandas objects are generally immutable, and operations on them are immutable. which, again, coming from pure Python land, you can append to a list or you can insert something into a dictionary, but like adding a row is somewhat painful in Pandas land. So this is how you do it, and so I'll explain what's going on here. There's a function called concat in Pandas, and it takes a list of data frames and appends those together or joins them together. So we have the original data frame here that we're passing in, and we're creating a new data frame with my data in it, and we want it to join those together. Yeah.
Can you use the addition notation for that too? Like
Can you?
equals df plus p dot data frame.
Yeah, so the question is, can you say df plus this data frame, would that work? And no, it would not. It would try to do math on the data frame.
Oh, okay, that makes sense.
Question.
Yeah.
Instead of concat, couldn't you use append? I believe that's what I've been using.
Yeah, I think there is a method in there, append. So I guess you could use that too.
Syntax, if I remember correctly.
Yeah. In practice, I would have two data frames and I would concatenate them together, but I don't recall the syntax of append, if it takes a single guy or not. Anyway, like I said, there is more than one way to do it in Pandas too, which as a pure Python guy I find annoying, but that's just the way the library is. So I don't mean to rag on Pandas, though it appears that I am, just sort of opening your eyes to what's out there. Okay, so if I want to add a column, so adding a row was sort of annoying, but if you think about it, I went into all this stuff about how it's vertically oriented. If you think about it, then it makes sense to like add something to every single column is somewhat of a pain, because now I've got each of these objects I need to add something to. Versus if I'm doing row oriented, it doesn't really it's not a problem to add a row. Similarly, because I'm vertically oriented, adding a new column isn't really that hard. And so if I say df test3 equals 0, and again, this comes back to, so some people have said that the data frame is like a dictionary, because this looks like a dictionary, right? This looks like dictionary assignment here. What this is doing is saying, create a new column, test3, and set every value in that column to 0. Which, if you're coming from pure Python, that's maybe confusing, but that's what's going on here. So it's adding 0 to everything in the column. Okay, and note in this case, if you say df.test3 equals 0, the attribute assignment doesn't work there. Okay, it only works in the index assignment, but attribute assignment doesn't work in assigning values into a data frame, which is just a gotcha, I think. It doesn't behave similarly both ways. Okay, so, but that's pretty simple. If you want to add a new column, you can do that pretty easily. You can also add a column based on a function. So if I want to say test4, and I have some function that determines test4, and say I want to determine test4 based on the first name. So maybe I'm doing some silly arbitrary grading, but I'm saying take first name. This is a series. This is my first name, which is like A, B, C, or D. And I'm saying apply a function to it and assign the result of that application into the column test4. In this case, I'm applying this function grade, which takes a value. So apply will call for every value in this series. We'll throw it in here, and I'm going to return. So in this case, it would be a string with a character. I'm going to take the first character of that string and return the ordinal number and use that as a grade. So it's a silly grading system, but it's an example of how I can call a function to create a new column in my data. And a lot of times, when you're munging data, you're going to say, I've got this column in there, and I've got this other column in there, and I want to create a new column or merge those columns based on some application of a function between them. And this is how Pandas allows you to do that in Python rather than going out to Excel or writing something in SQL to do that. So that was based on a single column. You might want to do it with multiple columns. In this case, we're calling apply, and if we say df So we're creating a new one, test 5, and it's going to be based on test 1 and test 2, and it's going to call this average grade on it. So if we say df, and we have 2 square brackets here, so basically we're saying dereference df, and inside we're passing a list of column names. Rather than returning a series, what this is going to return is a new data frame with just these 2 columns in it. So this is saying, take this new data frame, apply this function to it, and go across axis 1. So I remember I talked about axis 0 and axis 1. Axis 0 is your index, axis 1 is your columns. If I say axis 1, then it's going to say, when I call average grade, it's going to give me values, and it's going to give me test 1 and test 4 for this going across axis 1. Otherwise, it would give me the values going this way by default in axis 0, and so it would be too many values. It would give me all the row values. So that doesn't really make sense in this case.
Can you get crazier and do like an axis 2 and like pages?
Can you go to axis 2, like go from bump up to level 11? So in this case, there are only 2 axes. If you go to the 3-dimensional one, it has the 3rd axis. But like I said, I've never seen anyone use more than 2 levels of axes. So
I like previous presentation, I'm like, NumPy was like, well, yeah, you can have like as many axes as you want. And I'm like, well, if it's NumPy back, maybe.
yeah, pseudo NumPy backed.
Okay.
I don't know. You could try it. I'm trying to think of what it could do. There might be some justification of how it would work. I haven't tried it, so
Get back to you.
yeah. Okay, so we talked about adding a column. Here's some ways to remove a column. So we can say pop, and we can say del df.test. So again, this is where people say it's like a dictionary. I don't think of this data frame structure as very dictionary-esque, but it supports this del statement in this way. And again, there's an incongruency here where you can say if you do del on attribute access, it doesn't work only that way. So, yeah, question.
But all operations will work with the square bracket instead of
Yeah.
X access.
Yeah, the comment is, if you use this, you're going to be safe. This could bite you, and I say this because I had instances where it bit me, and the code wasn't working, but it didn't complain. So, and another thing to note is that pop is an in-place operation, whereas generally most operations on data frames return a new data frame, but pop does not. So this is one of those other ones where if you're normally, when I was doing data frame manipulation, I would say like data frame equals the result of some data frame operation, and I'd say df equals, and then in the line below I'd say df equals the result of some data frame operation, and the line below I'd say df equals again. If you do that with df pop, then you're going to get the series that came out of that column. So that's just a gotcha that you should be aware of. So you can rename columns as well. There's a rename method. You can pass in columns, and it will say, okay, I want to rename the column F name to first and last name to last. And here I'm doing what I just said, right? df equals df.rename. And that's generally how I would use pandas. So now I have something like this. I can say sort as well. So sort by the last name, and ascending equals false. And so you'd have something like this, and you'll note that like now my indexes are going this way instead of that way. Again, a difference from Python land. In Python, sort is in place. In here, it's not in place. It's returning this data frame now. So just, again, trying to burn in the differences here. You can do row iteration. So there's a method called iterRows, and it returns this tuple of the index and the series in the row. So in this case, when you do row iteration, it takes the row and converts the row to a series. So it's taking each value out of those columns and throwing all of those values in there and making a series. What this guy down here is doing is it's trying to update values in the data frame. So it's saying if the last name is M, update the value. And you're given a series here, but if you update it in this series here, this is like a view into that, but updating that view doesn't push it back up to the original data frame. So this wouldn't actually update it, but calling def.setValue, so setValue is a method that takes an index and a column and a value and inserts that into the original data frame. This guy would work. So luckily, because iter_rows gives you the index, you have that index and you know the column that you want to update, and you can update that value there.
Quick question.
Yeah.
So does that work like a, does it return the whole result set immediately before it starts operating on that, or can you, so if you had like millions of records that you're returning,
Yeah.
that's going to take a long time to start?
So it's an iterator. It goes row by row. Yeah. Okay, so after this, our new data looks something like this. I should note that now, if you note the index here, I have repeating indexes. So that might be something else that might bite you. When I concatenated my Matt guy on there with my other data frame, when I created Matt, he had an index of 0 because that was the default index for him. And when I throw those together, Pandas doesn't care. So if you start doing stuff on your index and aren't aware of that, it could bite you. That's another thing that may or may not bite you. Again, I'm not trying to sound super harsh about Pandas. I'm just trying to like open your eyes. This is what it does. If you're from Python land, it may confuse you in some places. Comment or question?
Yeah, what does it do when you have ambiguous indexes? So you're using indexes.
Yeah, so the question is, what happens? Well, if you do an index operation, sometimes it will return a scalar, or sometimes it will not return a scalar, right? So in this case, if I pull out the guy index 0, it's going to return both of these. But if I pull out index 1, it's only going to return one value. And so actually, the operations can return different data types. And if you're programmatically processing what you're pulling out of an index, it might fail unless you're checking the data type, which could be annoying.
Sounds like you don't want to use the index for anything context-wise.
You might, because index is very important. When we see plotting on the x-axis is all based on index. So you just have to be aware of that.
Right.
And you can update the index and change it. If you say ignore index, when you call the concat, there's an parameter called ignore index, and you pass true into that. It's on this cheat sheet too. It will update the index, and so it will be incrementing and won't have duplicate indexes in there. So we talked about filtering a little bit. We talked about Boolean indexes. Again, just to rehearse this, I say the type of, I have a data frame. The type of one of the columns is a series. If I put 2 brackets around it, that's saying pull out this list of columns in there. And if you pull out a list, it's going to return a data frame instead of a series. And so this here is a data frame as well because it's got 2 columns that you're pulling out. So even though these have the same, this has the name of test 1 and this has column test 1, this one's a series and this one is a data frame with 1 column in it. And they're different. One's 2-dimensional, one's 1-dimensional. Okay, filtering rows by Boolean vectors. I can say, I can create a mask. I can say, take this column test 2, and make a Boolean vector of greater than 85. So is this greater than 85 true? True, true. In this case, it doesn't, well, sorry. So greater than 85 on test 2. So we filtered out these guys and this 60, right? So that's what happened in that. So I can also create vectors based on functions here. Remember I talked about apply, so I can pass in a function in there, and I can return a Boolean here. That will create a Boolean vector, and I can apply a mask with that. You can join together your mask, so I can say this mask or that mask. I can say this mask and that mask, not equals true. Note that this not mask does not work. So, but in general, there's a lot of power there, and you can do that pretty easily. You can create these masks where you can say, okay, I want all the rows where this was greater than this, or this value was equal to this string, and this column over here was greater than this, and this happened on this date. And you can join these together really quickly, something similar to what you would do with SQL. Okay, if you have not in numbers, sometimes you're going to have junk data. You can deal with those. So in this case, we had test 5. So if you see here, test 5 had a not a number in here. I can say update test 5 and take test 5, the series, and call on the series fill not a number with 0, and that just puts a 0 in there and update that with there. So you could say if you have not a number, you could put -1 in, or you could put some other value in there. And that, in general, statistical functions ignore not a number. So if you want to take those into account when you're doing summary statistics or other processing, then you want a real number in there. Okay, joining data, you can do joins similar to database joins. So again, like I said, Pandas is sort of SQL-esque or NoSQL. So if I've got another column here that has first names here, and then a mapping of real names, so it's got letters and then real names, and I want to join that, I can say pd.merge my original data frame with my new data frame. Both of them have a first column, and it will return this. I can add a how equals left. This does a left outer join. So in this case, only the ones that matched up on first here would be returned. And so only A and D matched up. This P, Paul, wasn't in my original data frame. If I do a left outer join, then it pulls everything from DF and joins it with name MF and leaves not a numbers for the other ones.
No, go ahead. Can you do theta joins?
You can do right joins, you can do full outer joins. So yeah, basically whatever you could do with your database, you're good.
So one thing that I haven't really been able to get straight is there's pd.merge and then there's pd.join. And
Yeah.
they seem to do about the same thing. Do you know the distinction between them?
Oh, yeah. In general, I've been using merge, so I don't know. Again, this is one of those things where there's like multiple methods that do more or less the same thing. I'd have to look into that. We can look into that after, mess around with it. Okay, so in this case, so you notice this one had first over here, and it created this new column name over here. In this case, I'm just saying, okay, now you've got this name. I want you to put it back into first and fill the NA values of name with first if they're there. And so that does this sort of swap in place. So this is like an update where in SQL, where I say, select this, update where this. And you can also update with dictionaries as well. So if you have some mapping from key to a value, I can call map on it, and I can pass in this mapping, and it will update as well. Okay, I think we're actually out of time, so I can cruise through the rest here, or you can feel free to leave. Grouping, you can add groups. So here I'm just going to add a teacher. We just add this teacher alternating here. And then I can say df.groupByTeacher, and it will say, okay, I'm going to summarize everything that's a value or numerical by teacher and get the median of it. And it gives you this sort of simple pivot table really quickly by doing group by. I'll add an age column, and now I can say group by age and then group by teacher, and now it gives me this index here, which is called a multi-index in Pandas, where it has more than one level in the index. So it's saying, okay, I've grouped by age, here are the 14-year-olds, and here are the 2 teachers, and here are their mean scores. So to take that further, you can create pivot tables as well. So if you're familiar with Excel, you can do pivot tables in Excel. You can also somewhat do those in SQL as well, but whoever can remember that syntax is beyond me. But it's somewhat straightforward in Pandas. You say pivot table, you pass in data frame, and you say, these are the rows I want. So I want rows to be teacher, so it's going to put teachers out here, and I want columns to be age, and then I want values to be test 1, and it will give you all the values of test 1 by teacher and age, and put them in there and fill not in numbers that way. And then you can say add summation columns, margins equals true, and it will add these summation columns, and you can say to sum up them, use the mean, and sum up the mean this way, and sum up the mean this way. So that's pretty cool, right? To do that with that few lines of code. Okay, serialization, you can spit out to CSV. That's sort of the lingua franca, I think, of data science. But you can also do Excel, dictionaries, NumPy matrices as well.
So that prints to a file when you do that?
So in this case, I'm making this Python string IO guy that implements a file that's a string buffer. But if I had a real file here and I said to CSV and I had a real file handle with open, it would write it to the file. So plotting, it has support for matplotlib built in. It's not super pretty. Matplotlib itself isn't super pretty, but it can do it. Here's some boilerplate. So I create a matplotlib figure. I create an axis on this figure. An axis is something where you draw to. And then I can say data frame, group by age, take the mean of that and plot that on this axis. Here I'm just saving it, and then I'm clearing out the figure because I'm going to draw other ones. And it would do this. So I grouped by age, and it made an index here of ages. And then I took the mean values of my tests here, and I plotted those. So for test 1, at the ages, those are the mean values of that, which is pretty cool, right? Now I can plot that way. If I wanted to plot the median test scores, then I need to have, so again, the x-axis needs to be the index here. So I'm going to say df, take all my tests, take the median of those, and then I call this t. That does a transpose. So in this case, I've got data frames with test 1, test 2, test 3, test 4, test 5. In my columns here, I take the median of those. That collapses them up this way, but I need the index to be on the x to plot it. So I call t, which transposes my matrix, flips it over this way, and I call plot, and I get something like that. So now I have my medians for all my test scores. Plotting, box plot, I can pull out my test scores and do a box plot of them. Pretty simple. Using name as index. So here I'm saying set my index to my first name, pull out these columns and plot those as a horizontal bar chart. I'm going to plot 2 of them actually. In this other one I'm going to fill NA with 50. So you'll see that this NA was 50 and it's 0 over here, not existent. So this is my last example. I'm sorry for if I'm running over, feel free to leave. So I like skiing a lot. I went up to Snowbird. I took my phone and I tracked when I started skiing, I tracked what I was skiing. And so I just did this afternoon after lunch. I'm like, okay, let's give a real example of like, everything I had was sort of toy data, and this is like real data that I pulled out of my phone this afternoon and plotted it. So when I went to my phone, I said, okay, this is my KML data, which Google keeps track of. And this is, I'm going up the lift at Snowbird, and then I'm skiing down, and those are all my routes. So in my phone, I can export it as CSV, but because I want to be enterprisey, I exported it as KML, which is XML, right? So we'll show you how we would parse XML. The XML looks something like this. It's got boilerplate for XML, and it's got a bunch of junk in here, but you dig down 100 lines or so down, you find something like this. It has this track element, and then it has a win, which is some date string, and then it has a coordinate, which is latitude, longitude, and optionally an altitude in there. So sometimes your phone gets your altitude, sometimes it doesn't. Anyway, here's how I parsed it this afternoon. I got an element tree, I passed in my file name, I got the root. I'm going to collect the results of these guys. So basically I want to pull out a timestamp, latitude, longitude, and optionally altitude into like a tabular format here. So I find all these track parents, and I'm going to iterate over the child of them. One of them should be a win, the other one should be a coordinate. So I'm just going to get the text of the win. The coordinate, I'm going to map float to the split of it. So splits it on space. If you look at it, there's space in between here, so I'm going to split it on space. I'm going to make it into a float. I know it's going to have latitude and longitude. It might optionally have an altitude if the length of that was 3. I'm going to make a dictionary that has win, latitude, longitude, and altitude, and append it into this result. And at the end, I take a data frame and throw that into my data frame. And now I've got all the data in my data frame. Does make sense? So, so I loaded this KML file. I call pd.toDateTime. So if you look at my datetime here, I just threw it in as a string. Pandas by default isn't going to try and coerce that, but I can just say toDateTime on this column and assign that back to the column, and it will do some magic and create a Python datetime from it, which is nice. I create my figure, put my axis in it, and now I've got this guy. It has a default index, but I want to graph on by time. So I'm going to say set my index to time, so down here is my date, and I'm going to plot my altitude over time, so altitude over time, and it looks something like this. So I don't know, I thought that was kind of cool, right? This is data from my phone that I pulled off this afternoon, and now I have my altitude over time. And it's not the prettiest. Like I said, Matplotlib out of the box isn't super pretty, but it does the job, and you can make Matplotlib pretty. So here I'm going to clip altitude. I'm just showing some features of data frames here. So I can say, or of a series, I can say clip. I want to clip on a lower bounds based on the quantile, this 2%. So if you look at this, I've got this would be my 0% altitude, and then it would go up to 3,500 meters or so. And so for some reason, when my sensor wasn't on, it went at 0, but if I go above that at 2%, it's going to be somewhere up here. So I'm going to clip based on that. So I can put any arbitrary number into quantile in here, and it will give me the 50th percent quantile. I'm going to take this 2% quantile, and I'm going to clip the lower numbers to that. So it will shift all of the zeros up to that lower number here. And then I'm going to convert meters to feet because, hey, US likes to be different and use weird numbers. And so I'll plot that, and now I have something like this. So it basically clipped all these, so it didn't. Now my graph looks, I don't know. I would claim that I like the angles of that better, but I don't like these telling off things. So if I were going to do this in real life, I'd probably squish the graph down to make it look better. But
can you flip it as a way just not to have it put a value there, so it doesn't fill in the gap?
Yeah, I could say set zeros to whatever number I wanted to if I wanted to. To clip this way. Yeah, you could do that as well. You'd have to do something. So here I'm going to plot all the things. So I set my index to win, and I just say plot, and I'm going to use a secondary y to plot latitude on secondary y, which is sort of weird. So here I'm plotting altitude here. Here's longitude, and because my scale is blown out here, my longitude looks flat. But I plotted latitude on the secondary y, and you can see that my latitude's sort of going all over the place. But most of us don't think in latitude. So I looked up how to convert latitude to speed and distance after lunch, and I got some formula that was written in C, and I converted it to Python really quick, and it goes down to here or something. But basically, I threw that in, and so I clipped it, and then I got my total distance. This guy, that previous slide added my distance, this distance guy and its speed, and I got my total distance, which is my cumulative distance, and I'm calling Pandas rolling mean using 60 samples to get my average speed. And basically I'm going to plot my altitude, my speed, and my average speed. And then I get something like this, where here's my altitude, here's my speed samples, and these are pretty fine, so they could sort of be up and down. But if I average those over 60 measures, then it looks somewhat normal, right? And then this is by time. Here I'm just swapping out my index by total distance here, and now I can see at this time at this distance how fast I was going rather than at time. So these aren't the prettiest. Like I said, I did them at lunch, but it gives you sort of a feel for, in this number of lines of code, I could tweak that data and have something that might give you insight into what you want to look at. Anyway, that's all I have. If you're serious about this, you probably want to look into IPython Notebook, which is like a notebook that will allow you to interactively update stuff on the fly. SciPy is a scientific library that has some support for integration with pandas, and you can do scientific processing on top of that. Part of SciPy is scikit-learn, which is machine learning, and there are libraries that have links to do machine learning, so you can do classification, clustering, regressions on pandas data frames, which is pretty nice. And if you're looking at stats, there's a stats model which will allow you to create stats model in an R syntax. The question over here about R versus pandas. So basically, pandas has gone and ripped off the data frame from R. So why would you want to use R versus pandas? Because Python is a better language. Having said that, R has some more statistical libraries that if you're used to those and you're an R shop, go ahead and use those. It appears that in the data science world in general, people are moving, R is popular and people are moving towards Python because it has generally a better ecosystem than R. So if I'm doing like XML processing or a database, or I have to scrape some, I have to pull data off, Python has tools to do all of that really easily. If I wanted to talk to a database, make a web server, Python can do all of that. R can do most of it too, but it's just not, that stuff isn't the focus of R. The focus of R has been statistical processing.
I did an apt-get install Python Pandas, and I noticed it downloaded a whole bunch of R libraries. I don't know, that could be just because there's a common statistical analysis.
Really?
Package.
On Ubuntu or on?
Ubuntu, yeah.
Huh.
Download like 10 of them R-dash.
Yeah, there might be, because there is a R to Python library, and I don't know if the default dependency says to do that. I don't think it did it on my machine, but yeah. Who all here is using Windows or something other than? Okay, no Windows. Some are Mac. Another thing about Pandas is it can be a pain to install because it's built on NumPy and Python, and so it's not just a pure Python install. A lot of times you have to have dependencies, so that can be a pain, like on Mac. On Linux it tends to be somewhat easier because you can sort of do the apt-get install and it just works. Yeah. Pip install will work if you have the C dependencies, but if you don't, then it won't.
Pip isn't very good at dependency.
So I would recommend if you're on these other platforms, Anaconda is sort of a Python meta distribution that's big but just splats everything down there and just seems to work.
I was just going to say, there's a project called PrettyPlotlib, which takes matplotlib and makes it look a lot like ggplot2 in R, so the graphs are a little bit nicer.
Yeah, that's a good point. PrettyPlotlib, there's another library called Seaborn. And I do a talk on Matplotlib that shows like you can create really nice Matplotlib guys, but it takes a little bit of boilerplate and default tweaking to have that happen. So that's, I guess, one of the nice things about R is that someone with some thought care to say, let's make the defaults look pretty because sexy sells and people actually care about that. And when you have something in R that comes out and it's like, oh, that actually looks nice, and you have something like this, it's like, oh, yeah, it looks like someone did that after lunch and forgot to like format that up there, and yeah, total underscore dist must be a Python person, and what's
that internal will be fired.
Yeah, so yeah.
And just from my experience, it's like R is better put together in its own sort of little box for the math, but at least for when I play with data, the hard part is never the math. The math that I do is never that hard that I can't do it in Python. The trick is always the scraping.
Yeah, the 80% is that you're spending cleaning up this junk, and joining data.
So versatile. Like you can go and crawl all over the web with it, and it just sort of shoots it into the same thing that you're going to be processing the data, and it's just awesome.
Yeah, there are some people who sort of use pandas and Python as sort of this first step, and like, okay, now I have a CSV. I'm going to use R to actually do fancier stuff on it, right? Use the packages, take advantage of it, but doing a lot of this cleaning and manipulation would be somewhat more painful in R.
Yeah, and I've just never needed the horsepower.
And I would say that Python is coming up on R. I mean, the statistical libraries are improving.
I think think Python's good, like you said, for production environments. It's a better language, but it depends on the background of the person too. So if it's more into software side of things, Python's much better.
Yeah.
But I'm more like a mathematician. I'm a data scientist, so I'm a statistician, so I just use R 100%.
Mm-hmm.
I force it to an extent that the production code is also running in R.
Really?
But it takes some effort from the DevOps to get everything set up for obvious reasons.
Yeah.
Yeah.
Interesting. So hopefully I haven't said anything that offended you as an R person.
No, I'm pretty open-minded here. So.
Okay. Another comment back here.
Oh, no, I was just saying we have some databases in Mongo that need to be output as CSVs, and so we use Pandas as a kind of a manual ETL process, and it just makes joining different data sets that we can't join in Mongo. It makes it really easy because I can, rather than just do the export. So
Yeah.
I just run a shell script and it imports and runs the Python.
Yeah. And I mean, like I said, Pandas provides a lot of the stuff that you could do in SQL, and I don't claim that like Pandas has the best interface, as you can tell, like how I've like sort of bad-mouthed a lot of it, but it gives you a lot of power and allows you to do a lot of stuff that, like, you know, if you're dealing with Couch or Mongo and you need to do a join, or they make you go through horrendous rain dances to do some things where it's like, okay, at this point I'm just going to pull it into Python and deal with it there because that's my hammer.
So, when you compare Python to other resources out there for doing similar things, I mean, you probably could use, you know, NumPy plus matplotlib, you know, and kind of get the same thing, you know, with a couple more keystrokes. What, like, is there anything that that Pandas kind of like is in competition with?
In the Python world, per se?
Yeah.
I mean, yeah, people have been hacking stuff like with NumPy, right? NumPy support for strings has kind of not been a strong point. This whole notion of index and joining things by index on this left side is, you could claim that that's a power of Pandas that NumPy out of the box doesn't give you. String support in NumPy is just really weak relative to that. As far as like ETL, if you're doing pure ETL, I would say there's a Python module called Pygram ETL, which has good support for like slowly changing dimensions and doing ETL workflows and saying, I've got this, I want to throw it through this and throw it through this. But generally, when I'm doing ETL, I would use like Pandas on the front end to like clean everything up first, and then use Pygram ETL to start doing my ETL process to actually throw into the database or the data warehouse.
So you might say that sort of Pandas is sort of the most
it's your workhorse
in this space.
Yeah, like I said, it's like the Perl regex, right? I mean, you have tabular data. Unless it's numerical, I think Pandas is probably the best tool out there right now.